All right, so we're going to finish the lecture where we left off, which we had looked at cash flow diagrams, and now we're going to look at using the compound interest tables. And using the compound interest tables is a very, very quick way for us to avoid having to do some pretty gnarly calculations. And so as we look through different types of cash flow series, the different calculations by hand would get more and more complex. And so there were compound interest formulas that were inputted, automatically calculated, and then given to us in a wonderful table form that allows us to use these more easily. So some of the important information of how we're even going to talk about this is that we look at this idea about what's we're looking to find, what's been given, what the factor is called, and what that symbol notation would be. So really quickly, if we're looking to find F given P, which means we're looking to find the future given a present value, we could do this mathematically using the compound interest formula. This is what we saw. We did simple interest and then we did compound interest, and that is this formula right here. If we wanted to find P given F, we see that this is just the reciprocal of the previous equation. Now, this is why the equations can get pretty complex pretty quick, because as we continue to build on these, a lot of times we're taking reciprocals with exponents and the math just gets a little gross. So for F given P, we use the compound interest formula. The factor is called a single payment compound amount. And in factor notation, we see it's F given P. Then we have I for the percentage and N for the number of payments or number of compounding periods. Same thing for P given F. We have the reciprocal of the compound interest formula. It's a single payment present worth. And we see P given F with I percentage and N as the number of periods. So we're going to switch to the dot camera and look at a couple of these examples, as well as looking at the compound interest worksheet. So I'm going to switch to the compound interest worksheet over here. All right. So when we look at this worksheet, we see, first of all, that we have all of our ends going down this axis here. So we have periods that are going in single digits, 1 through 5, 6 through 10, 11 through 15, 16 through 20, 21 through 25, 26 through 30, 31 through 35, and then we start jumping up by fives. So after 35 periods, we're going to start going by fives, 40, 45, 50, 55, and we go all the way down to 100. Then going across the top, we have a couple different types of payments. We have single payments, we have uniform series payments, and we have arithmetic gradients. So our F given P right here, that is the compound interest formula, as we said, and our P given F here is that inverse or reciprocal of the compound interest formula. And so we can see the values for N number of payments for the F given P factor or for the P given F factor. Now note that the F given P factor, we see the time value of money increasing. So if I'm finding a future given a present, over time, this factor is going to increase. $1 tomorrow is worth more than $1 today. And so the inverse of that is also true. My present worth factors are starting at 0.9434 for 6% interest, and they are going down from there. So if I'm starting with a future value and I'm going to find a present starting with that future value, that present that I'm searching for is going to be less than the future value I started with. Now, to make sure that you're always using the right table, you look at the percentage. And so we've got 6% right here. We have these in the back of the book for all different types of percentages. You can Google them online, and I have it posted to our Blackboard site as well. So looking at this chart and looking at the problem at hand, we see that our problem is looking at find a future value given P with an interest rate of 6% and an N of 5, starting out by using the formula. So starting out using the formula, we're going to write that F is equal to P times 1 plus I to the N power. That's our simple compound interest formula. So that's $10,000, 1 plus 0.06 because of 6% to the 5th power. And that gives us F is equal to $13,382.66. So our principal is that present value, that $10,000. So we're paying $3,382.66 in interest at 6%. Now, to use the compound interest formula table, I would say that I'm going to find a F given a P, and I'm using the compound interest F given P at I% over N periods. So the F is going to be equal to $10,000 times my F given P factor at 6% over 5 years, or periods in this case. I don't think it says years. Okay, so 6% interest table. I know I'm on the right percentage. F given P factor, so it's this very first column. N is equal to 5, so 1.338. So 10,000 times 1.338, and F is equal to, we see the same amount basically. So we have that 13,380. So we're off by $2.66 by doing this using the compound interest table rather than doing it by hand. Really, that's pretty negligible in the world of finance. So flipping this, doing this for the present value, we're going to start with our F of 13,380 with an I of 6% and an N of 5. So the formula to find the future present given the future is the reciprocal. And so we have 1 over 1 plus I to the N power. And so we have, putting this in more standard notation, we have 13,380 is our future amount. And then I'm going to do 1 plus 0.06 to the negative 5. To take care of that reciprocal, I'll just negate it. So it's still that 5 in that N place, but I'm going to do a negative, and that way I can just put it all on one line because it's simpler to write that way. So I have 13,380, and 1 plus 0.06 to the negative 5th power is 0.7473, which gives me $9,998.87. Using the compound interest table, I can find P given F at I% over N periods of time. And so I have 13,380 P given F factor 6% for 5 years. So this time I'm looking in the second column, P given F factor 5 years, and it's 0.7473. Just as it was above, 13,380 times 0.7473. And so, of course, we're going to get the same answer because it's the same numbers. So again, we're off by like that $2.13 from the initial 10,000 we started with. Why? Because these factors are all truncated. So because we're rounding, I started here with 10. I did 6% interest over 5 years. If I did it by hand, I had this $13,382.66. Compound interest tables truncated that to 13,380. I reverse engineer that. So I take the reciprocal and I work backwards from that 13,380 going back 5 years. I should have $10,000, but I'm actually $2.13 short because this interest factor is the same as the compound interest table, as it always will be, although it might be a few decimal places off. We get the same answer both places. So we can also calculate n using the formulas. And we can see that if we wanted to find n given our values, we would just take the logarithmic function of f given p over the log of 1 plus I. These formulas are also in your book, and they are derived in your book. I'm not going to do the derivation here, but they the full derivation is present in your book, and the formulas are all in your book as well. So I have the log of f over p, and then I have the log of 1 plus 0.06. And so that is log of 1.338 over log of 1.06. And that is 4.997, or approximately 5 years. So I found my n doing the same method that this function here, that's looking at our f given p factor that we saw above. This here is that interest rate that we see, that 1 plus I. And the logarithmic factors in this equation then derive us to our n. And so we can find from these equations that we've gone over, p given f given p, or n given both f and p. So we can work the variables any of the directions. And the next video is going to go into sections 4.6 through 4.9.